Yeah, I found myself in the middle of Mokgopong, or Naboomspruit as it used to be called. I'm out here on business. I've managed to commandeer a restaurant which gave me Wi-Fi. So if there is a bit of noise, I apologize for that. What we're going to do is we're going to chat a little bit about gaskets tonight. When I do training and that sort of thing, I find it far more important to actually understand how things work, rather than quoting facts and figures. Facts and figures you can get out of a book or a manual or that sort of thing. So, we're going to talk a little bit about gasket properties, how they're important, where they benefit you on site, how they can actually solve mechanical and physical problems on site just by having a look and consulting the gasket properties. If you have a look at it, there's a couple of gaskets here. These are compressed fiber gaskets. If we have a look at the definition of a gasket, basically a gasket is any deformable material that's used to create a static seal and maintain that seal under various operating conditions. I enjoy definitions. They are very complex and they do define things well, but on the other hand, they've got so much information in them, you tend to easily overlook things. So if we have a look at a gasket, a gasket must be deformable. So if I take a gasket, I put it between two flanges, I tighten my bolts, that gasket must deform. It must essentially compress. It must get thinner. When your gasket gets thinner, the material on the face of the gasket moves around, flows around, fills the imperfections in the flange, and basically creates the seal you're looking at. Now, that in itself brings in a couple of questions. Obviously, your flanges, your fasteners, and your gaskets must work together in unison. Your fasteners develop the load. Your flanges need to take that load and evenly distribute it over the gasket so you can get an even stress throughout your gasket. When we get onto gasket load and gasket stress, it brings us to one of our first properties we can start considering is something called seating stress. Seating stress is basically the minimum amount of stress you need to apply to your seal area in order to get the gasket to deform, the material to flow around, and to actually create the seal. So seating stress is very, very important. The problem we find ourselves in is that on general plants, as we know them at the moment, are all full of standard sort of flanges. They've got equipment on there that's been designed prior to 2009. And in those days, CAF, the compressed asbestos fiber gasket, was the material of choice. If we have a look at the seating stress of compressed asbestos fiber, you find that seating stress is 11 MPa. When you have a look at your non-asbestos alternatives, they tend to be green, gray, that sort of thing. Your non-asbestos alternatives tend to come in with a seating stress of about 25 MPa. That immediately throws a spanner in the works, in that we now have to use a gasket material that requires a higher load or a higher stress in a piece of equipment or a pipeline that's been designed with a material that requires a lower stress. So understanding your seating stresses and what your target stress should be on your gasket goes a long way to actually help identifying what gasket you require. With that being said, obviously, stress is force over area. As the area, your seal area increases, so the amount of load you need on that gasket must also increase so you can develop the stress. When it comes from a design point of view, a lot of the guys, when they're designing a plant or designing a new pipeline, they tend to go for flat face flanges due to the cost issue. The problem with that is with a flat face flange is that flat face flanges have very large areas, very large seal areas, and they tend to have limited available bolt load. Those flat face flanges were essentially designed for the use of asbestos. So what happens when you have a flat face flange, you limit your choices, or you limit the materials you are able to use on those flat face flanges. And that sometimes has a performance implication. By the same token, we must also take into account that everything has a maximum and a minimum. So your seating stress is basically the stress you need to apply to that gasket to get it to seal. What you have to do is you have to look at a target stress, which is what you would have actually applied to the bolts to actually physically install that gasket. Your target stress is a stress that must be calculated. It must take into account your internal pressure of the system. Your internal pressure tends to separate the flanges, so it will remove load from your gaskets when you're getting up to pressure. You also got things like stress relaxation, which we'll discuss a little bit later, which is a loss of load due to embedment of threads, creep or cold flow of the gasket. And then, of course, you got your maximum allowable stress. At ambient conditions, you need to apply a stress to that gasket that's below the maximum allowable stress so that the gasket doesn't crush, but it must be as close to the maximum allowable stress as possible, such that after or post stress relaxation of that joint, there's still sufficient stress in the joint to give you a long-term seal. All right, you've got a couple of gaskets. These are compressed non-asbestos fiber gaskets. These things, they pretty much look like cardboard. They tend to be green, green in color, green and white, gray. They are manufactured from various non-asbestos fibers such as aramid, carbon fiber. We've got glass fiber as well. All are reasonably high temperature fibers. Your aramid goes up to about 300 degrees, your carbon fiber 450 degrees, and your glass fiber around about 400 degrees. Now, that being said, they're all high temperatures. With the fibers, we actually mix them in with a binding agent or binder, which is actually nitrile rubber. Now, nitrile rubber is essentially where the weak point of the gasket is. It does have limited temperature carrying capability, and these gaskets tend to fail when they're exposed to elevated temperatures for too long. My safe call on a temperature for any non-asbestos compressed fiber material will be about 180 degrees because you get about 3 to 4 years service life out of that gasket. If you raise that temperature up to about 200 degrees, you'll probably get about 18 months to 2 years. At 220, you're probably looking at about 6 months to a year. So as you increase the temperature, so the life expectancy of that gasket drops dramatically. And we tend to cut it off at about 180 degrees. Okay, part of the matrix of these compressed fiber gaskets, we've got our fibers, which gives it the mechanical strength to resist the bolt load and to actually hold together and create a pressure boundary. You've got your binder material, which is your nitrile, which basically glues all the components together. And then you've got a filler material, which is normally is precipitated silica, amorphous clay. You'll notice a lot of the non-asbestos materials have some sort of silica or sil name in them, and that's because it contains silica. Now, the silica gets involved in the matrix in that it helps stop that gasket from being permeable. All gaskets have a certain amount of permeability, which means if you're sealing gases, especially low molecular weight gases, those gases can find a leak path through the core of the gasket. And when you're sealing gases, or especially vacuums, you want that gas permeability to be as low as possible. Gas permeability is measured in a number of units. So when you are comparing materials, take into account what the units are so you can measure apples with apples. You know, when you're trying to seal gases or vacuums, the ideal sort of situation would be to use a material with a low gas permeability or gas tightness. You would also want to use a material that is thin as possible because that reduces the amount of leak paths that gas can find. And on top of that, thinner gasket materials have a better ability to withstand bolt load. So you can actually ramp up your bolt load to further densify that material to control that gas permeability. All right, so gas permeability in our material would be pretty much our C4400. That's the one we would go for because of its superior gas permeability values. Another important gasket property to have a look at is a thing called fluid swell. It's also known as percentage thickness increase. That's basically a measurement of how that gasket absorbs the sealed media. in our compressed fiber materials, such as these ones here, they're sealed with a nitrile binder. So basically, this is a measurement of how much that nitrile binder absorbs the sealed media. It's generally tested with fuels and oils. So if you're in a hydrocarbon business, you'd want to consult that fluid swell. What happens is the binder absorbs the fuel or the oil, it swells up and it weakens. So you want that to be as low as possible when you're sealing oils and fuels. So, you know, a lot of the times when guys select gaskets, they go in there and they say, right, well, let's have a look at it. You know, when we select a gasket, we have to look at the pressure that the gasket can take. We have to look at the temperature that it can take, and we have to look at the media it can take. All fair points. We do have to make sure that those are all in line. But when it comes to a practical point of view, the understanding of the gasket properties goes a long way in actually figuring out which gasket is the right one to go for. If we have a look at our chemical range of materials, generally in the chemical industry, we would want to go for some sort of PTFE material. That's polytetrafluoroethylene. It's a very chemically resistant polymer. The problem with it is it does suffer from stress relaxation, cold flow, or creep. There's very subtle differences between all three of those, but essentially, if you have a look at it from the broad base, they all essentially mean the same thing. What happens with cold flow or creep stress relaxation is you take a gasket, you'll apply a load to it, and what happens is the OD of that gasket starts getting bigger, the RD starts getting smaller. What happens is the material between the flanges flow out from the high stress areas to the low stress area, resulting in the gasket losing density. It also results in the flanges moving closer together and a loss of bolt load. Now, all gaskets are measured against stress relaxation or creep. It's known as your stress relaxation test. What we basically do there is in our compressed fiber materials, such as the last ones we spoke about, these ones here, we will take a test sample or a specimen, and we will put it into a rig or a jig, and we apply 50 MPa surface stress to that gasket. What we then do is we advance age it. So we would heat that gasket material up to 300 degrees. We'll hold it there for 16 hours, and then we come back and we measure the stress relaxation that has actually happened within that material. Now, here I've got a Klinger C4324. This is our economy grade gasket. What we have to be careful with economy grade gaskets is they are essentially recycled materials. They contain a component of mixed milled grade. So we take the offcuts from all the other sheets, we mill it up, and we introduce it into our economy grade. The practical implications of that is that it tends to have a lot more binder material, so there's a lot more rubber in there. It does have limited temperature carrying capabilities because of that added binder. It does have poorer fluid swell fluid swell characteristics, so it does tend to absorb more of the fuel and oil that you're trying to seal, and it does break down a lot quicker. When we have a look at stress relaxation, our 4324, which is green on one side, gray on the other, that gets tested at 50 MPa at 300 degrees for 16 hours. The test result is 20 MPa. So what that means is that it was originally stressed to 50 MPa. What happens after the test, we're now down at 20 MPa. What you can ascertain from that, from a design or practical point of view, is that over the lifespan of the gasket, you can expect to lose 60% of your bolt load due to stress relaxation or creep. So, you know, with that being said, obviously in high pressure applications, you want to have a look at stress relaxation, and you actually want to make sure that that stress relaxation is as close as possible to the original test value. That will give you an indication of how efficiently that gasket maintains the bolt load that was originally applied on the flange assembly. When we have a look at PTFE, PTFE has a very bad name when it comes to stress relaxation. Obviously, we can't test these materials at 300 degrees centigrade because they vaporize at about 260, or gas off is the proper term. So your engineering plastics will get tested at 150 degrees, and they get tested at 30 MPa because they are polymers. They can't handle a very high surface stress, such as what we do with the compressed fiber materials. For a virgin sheet of PTFE, when we conduct a stress relaxation test on that, and we test it at 30 MPa at 150 degrees for 16 hours, we find that that stress relaxation value comes back at 3 MPa. Essentially what's happened is during the lifespan of that seal, you've lost 90% of your bolt load. Now, you remove 90% of your bolt load from a flanged assembly, you're going to experience a leak. It is just going to happen. There's no way that it can actually stay sealing. What we do is we then take our PTFE materials and we stabilize them. So we mix in other chemicals. It's a little bit like adding bluestone to dogger. You then create concrete. You create a material or mix of materials with completely different properties. If you have a look at our TopChem 2003 material, which is a white material, it's stabilized with glass microspheres. When we do the stress relaxation test on it, unlike the virgin PTFE, which ends up at 3, your stress relaxation test ends up at 13. So you're probably losing about 55% of your bolt load, but still fantastic material and way superior to your virgin materials. The other good thing with the TopChem 2003, because the filler is glass microspheres, you can use it in strong acids as well as strong alkalis. So it's a very, very good chemically resistant gasket. Our 2005, slightly different. This has a stress relaxation of 25. So from 30, it drops down to 25. It maintains bolt load for a lot longer. So it gives you a longer term seal. But, you know, the thing is with gasket properties, is, you know, your way all the time. There's a certain amount of compromise that must be taken into account. You actually have to identify what is more important to you at any particular point. So when it comes to stress relaxation between these two materials, the white one here comes in at 13, the red one comes in at 25. Now, another property we have to look at is compressibility. Compressibility is a measure of how much that gasket compresses or reduces in thickness. Now, right in the beginning, we discussed about how it's around, and it actually fills in the flange and creates the seal. Now, if we have a look at these two, even though the 2005 has session because it has limited compression, the 2003 has fair to good stress relaxation values, but generally in chemical pipelines you do end up with flange damage, and with the compressibility of 18%, this gasket can very effectively seal those flanges. So, yeah, with that in mind, there is another product that we have, which is a modified PTFE. This is our high-grade LS material. It's the biaxially expanded PTFE. Nice thing about it, it is extremely flexible. Okay, it's a bit like comparing your rubber on your car tires to the expanded foam you wear in your flip-flops or slops. So this material here has a compressibility of 60%. So basically when you compress this will compress by about 1.2 millimeter, a 3 millimeter piece of material, and it will very, very effectively seal worn or damaged flanges. My standard sort of remark here is if you can't get this gasket to seal the damaged flange, your best bet would probably be to weld it. Okay, so compressibility does play a very important part when it comes to gasket properties, especially when you're actually having a look. And a lot of the plants that we're working on these days do tend to have a lot of damage on your sealing faces. All right, that brings us to another set of materials, These materials are reinforced graphite materials. They're manufactured from graphite and stainless steel. There is no rubber binder in them, so their temperature carrying capability far exceeds that of your compressed fiber materials. These gaskets can go up to about 450 degrees. At 450 degrees, what happens is the graphite essentially reacts with the oxygen in the atmosphere. It forms carbon dioxide, and it basically breaks down. What happens there is you end up with a loss of density within your gasket material, and over time you will end up with a leak. At 450 degrees, that reaction rate increases exponentially. So normally, from a practical point of view, we wouldn't really use these sorts of materials at temperatures above 400 degrees. They also have very, very good tensile strength. Now, tensile is it's a funny problem. Essentially, tensile strength is very important when you're looking for gaskets that are resistant to blowout. Now, blowout is where the internal pressure overstresses the gasket breaks apart and actually forced out the side of the flange. So when you're working in high pressure applications, you want to choose a gasket with a very, very high tensile strength. These materials were developed in about I think they were developed in the 1940s. They didn't really take off in those days because when compared with their compressed asbestos fiber materials, they were deemed to be way too expensive. These days, they're actually quite economical. They have probably the best mix of all the gasket properties we have. They can handle high temperatures up to 400 degrees. They can resist pressures up to about 150 bar. The compressibility of these materials is sitting at 35%, so very effective at sealing damaged flanges. When we have a look at the stress relaxation, when tested at 50 MPa at 300 degrees for 16 hours, the stress relaxation on your reinforced graphite materials come in at 48 MPa, which means you only essentially lose 4% of your bolt load over the lifespan of that gasket, which is brilliant. Ideal for high pressure applications and high temperature applications. I think one of the more redeeming features of these materials here as well is their seating stress. Now, let's compare it to a couple of the other materials. We mentioned that compressed asbestos fiber had a seating stress of 11 MPa. Your non-asbestos compressed fiber, non-asbestos fiber materials have a seating stress in the region of about 25 MPa, 2.5 times that of asbestos. Your stabilized PTFEs, the white one here, which is the 2003, has a seating stress of 6 MPa, which is fantastic, very low. And the 2005 has a seating stress of 10. The reinforced graphites have a seating stress of 6 MPa. So these are all fantastic materials. Where you're having problems or where you've got applications with flat face flanges, what you want to do is recommend a gasket that has less than that of asbestos, so that we can maintain the original design of that. So we will get our telephone number and email address in a fantastic material. It is known as a problem solver, and it does work extremely well. When compared to some of the rest of the materials, this material is reasonably inexpensive. You can pretty much pick up your your reinforced graphite gaskets for about the same sort of price as your compressed fiber, and the performance of those materials far outweigh those of the compressed fiber materials. All right, that's pretty much it for your sort of seating material, your sheeting materials. We then move on to things like our semi-metallic materials. Our semi-metallic gaskets have a much higher percentage of steel in them. They tend to have soft compressible sealing faces. I'm going to talk about your spiral wound gasket at the moment. A lot of the other ones have very specialized uses, but your spiral wound gasket is a gasket that's made from lengths of stainless steel strip, 5mm wide. They're about 0.18mm thick. And what we do is we roll almost a chevron groove, or how can I say, profile into the stainless steel winding strip. We then spirally wind that together with a filler material around a mandrel or around an inner ring, and we actually build up your seal area of your gasket. The nice thing about a spiral wound is that with those multiple turns, or that spirally wound stainless steel, what happens is when you put it between two flanges and you tighten it up, you compress that spiral wound by 1/3. It's very important that whenever you use a spiral wound gasket, that the compression of that gasket is limited to 1/3 of the original thickness. What essentially happens there is when you compress it, you essentially energize the seal element. So all those spirally wound, chevron-shaped windings or turnings within that seal element now get energized. They start acting like a spring, which means that when you have things like cyclic service, if you've got temperatures that are low and then they climb up and then they drop down again, what happens every time temperature increases, your pipework expands, your flanges push together. Every time you lose temperature, everything contracts, your pipework pulls apart, your flanges pull apart. Now, what happens there is you must now choose a gasket that has very high recovery or resilience. Recovery or resilience is defined as the ability to regain something lost. So it basically measures how effectively that gasket bounces back and maintains the seal. If we have a look at things like our compressed fiber materials, typically the recovery of this, when calculated in millimeters, is about 0.15 millimeter. Now, when I say when calculated, your compressibility is measured as a percentage of the original thickness of the gasket. When you have a look at recovery, recovery is measured as a percentage of how much that gasket compressed by. So if your gasket compresses by 10% and you start off with a 3 mil gasket, your compression will be 0.3 of a mil. If the recovery is 50%, it'll be 50% of the 0.3. So that's how much that gasket will bounce back to maintain the seal where we've got movement in the flanges. If we have a look at our reinforced graphite materials, when calculated, this comes out at about 0.21 millimeter, so better recovery than your compressed fiber materials. And when we have a look at spiral wounds, because of that inner spring, because it's almost mechanically assisted in recovery, that recovery is 0.5 of a millimeter. So essentially it's 3 times better than that and 2.5 times better than those materials. And it's the ideal gasket for use in applications where you have thermal cycling, pressure cycling, vibration, where the bolts can start working loose, you can start losing bolt load. All right, so spiral wounds, fantastic gaskets. One word of warning when you are using spiral wounds, please use high tensile bolts. They do have quite a high seating stress of 69.9 MPa. It must be realized that the seal area of a spiral wound is a lot smaller than the seal area of a soft cut gasket. So those do kind of cancel each other out. But when using spiral wounds, we need to pay specific attention to the amount of bolt load we have, and we need to ensure that we have adequate bolt load within the flanged assembly. Of late, I've noticed a big shift in the way plants are designed and the thinking of the engineers when they're getting involved in plant builds and designing. And often it revolves around the stainless steel side. You know, people think stainless steel is very strong. They think it's a fantastic material. However, when it comes to gaskets, flanges, sealing, fasteners, stainless steel isn't that brilliant. It has a very, very low yield stress, so you battle to develop load within your flanged assembly. And if you do tend to overload these fasteners, what happens is they do yield very quickly, or when they do yield, you find that they deform the threads within the nut. And when it comes to loosening that nut, you find that the nut actually welds itself to your stud bolt thread. And that's just a result of friction. But the problem comes in is that the guys don't control the load they apply to a stainless steel fastener, and they essentially even realizing they're doing it. As far as we recommend, we would not use any grade of fastener less than a grade 8.8 in a flange assembly. And if we're using stainless steel, the minimum sort of strength stainless steel we use in a flange assembly would be an A270 or an A470, depending 304 or 316. We wouldn't go anywhere near the A240s, 50s, that sort of thing. They just do not have sufficient yield stress to develop the load we need to compress our gasket. When we are selecting flanges for a new plant or something like that, there's a couple of rules of thumb we like to put in. Wherever possible, try and select a flange with a raised face. What that does is it concentrates your bolt load over a smaller seal area, thereby helping you develop the stress that you require to actually get that gasket to seal. What it also does is enables you the use of a much wider, broader range of gasket materials, types, and styles. So you can actually now choose a gasket that would best perform and best last in your sort of application. We've also found that when it comes to stainless steel flanges, especially when they're fitted with stainless steel fasteners, the guys tend to shy away from the class 150 range, your ASME B16-5 class 150. A lot of those flanges do have limited available bolt load. Things like your 3-inch, your 6-inch, your 8-inch, your 24-inch do have limited available bolt load. And being stainless steel flanges, you're now using stainless steel bolts. That exacerbates the problem, and you can end up with fluid sealing problems on site. What the guys normally do is, if it is a class 150 line, and they would normally then recommend a class 300 flange that actually goes in, which actually gives them more available bolt load and enables a better seal. All right, so sorry, that was a crash course 101 on gaskets. As I said, I do have my telephone number and my email address up there. If you guys ever wish to just give me a call, want to chat about something, you have any ideas you'd like to throw around, please feel free to contact me anytime. Always available, always looking to help. As a company, we can supply all your gasket needs. We can not only do that, but we can help you recommend gaskets in any designs, projects, or any sort of applications where you're having difficulty on site. We like to think of ourselves as a cradle to grave sort of company. So we won't only supply you with the gasket. If you require a torque value or anything like that, we can assist with that as well in supplying calculated torque values for your specific application. So yeah, Gus, pretty much done with that. Are there any questions?
Yeah, thanks, Ryan. Let's see if maybe just from a practical point of view, I think we're a small enough group to treat the questions or to give the questions verbally. But what I just like to do then is, if you do have a question, just pop it in the chat, your name, then I can see, just say something, and then I can see your name, and then I'll just, so we can have some sort of order. So please feel free to ask the questions. I see Gareth. Gareth, he has a question for you, Ryan. Gareth, go ahead.
Hi, Ryan. Thanks for the talk. It was a lot more illuminating than I suspected on gaskets, having never dealt with them. But my question is about the manufacture. Where is it actually made? Where are the components made, and what portion of that, I guess, is local?
Okay. Well, we've got a factory up there in Wadeville. We've also got satellite manufacturing facilities in Durban as well as Cape Town. The compressed fiber materials are all manufactured locally in Wadeville. We've got 14,500 square meters under cover. We produce about 1,700 ton a year of compressed fiber material. Obviously, the exotic fibers are imported where we can, such as our fillers and our rubbers and our binders and that sort of thing are all locally sourced. Yeah, we manufacture our own gland packing as well. So that's all manufactured locally. We've got 42 mechanical gland packing braiders within Wadeville. We manufacture about 450 to 500 ton of gland packing a year as well. We've got a big gasket manufacturing facility as well, also in Wadeville as well as Cape Town and Durban. We've got small little facilities and a couple of the other branches just for the emergency stuff. But you know, you can't really measure that in ton. But from a turnover point of view, we produce between 18 and 19 million rand a month of production out of those gasket manufacturing facilities. Obviously, with with having that amount of material moving through your plant, we do have the ability to move and get quite technical and support the guys in what they need. So, you know, if you guys do need any training on site, be it gasket fitment all the way up to gasket selection, design, that sort of thing, we can gladly help with that, and we'll come in there and do it for you guys free of charge.
Okay, that's I didn't know it was that prevalent locally. Do you compete internationally, given the tonnage that you can produce?
We do export quite a lot. We make the biggest sheet within the Klinger group in South Africa, so we export to the United States, we export to the UK, we export to Australia. Klinger is quite a big company. They pretty much on every single continent. We've got 35 manufacturing facilities around the world. So yeah, we have a fair footprint within the fluid sealing industry.
Okay, awesome. Thank you for the presentation from my side.
Right, Ryan, just a question maybe from my side. You mentioned at the start when you started with Gasket, you said prior to 2009. Why is 2009 relevant? Important.
Yeah, in 1999, the government propagated the ban of asbestos, or CAF, compressed asbestos fiber materials within South Africa. They gave the industry 10 years to work through a plan of change. And what essentially happened there is, you know, a lot of the guys, you know, they'd go, okay, well, this is CAF, it looks like cardboard, it's got asbestos in it. And a lot of the guys were given misinformation that, you know, instead of using the red one, use a green one, and it's exactly the same. Yeah, the thing is, your non-asbestos materials are not exactly the same. If we have a look at it, your CAF material sealed at 11 MPa. It had a maximum allowable surface stress of about 200 MPa. So, you know, you had quite a wide target area. When you have a look at your compressed non-asbestos materials, these things are seating at 25 MPa, and their maximum allowable is sitting between 60 and 65 MPa. You know, it's a very fine line. You know, you've got to make it tight enough to seal, and seal for a long time, but not so tight that you crush it. And it ended up that a lot of the plants and a lot of the industry were actually having very serious problems with getting things to seal, because there was just a lack of understanding. And it's from then that we started developing our technical expertise and helping support the customers and recommending the right gasket materials and making sure that when you do select a material, you take all the gasket properties into account, and you make sure that that will actually work for you, or work the best for you in that sort of application. And it changed a number of things, the way industries were working. In the asbestos days, you know, guys just used to grab a 4-pound hammer and a flogging spanner and just go beat the hell out of it. With non-asbestos, it becomes a bit more complicated. You know, you actually have to start doing a lot of homework. You actually have to start managing the your joint integrity on site. It can't just be hit it with the hammer. And that's why I said prior to 2009, you know, your CAF was a very forgiving gasket. Basically, you threw it in there, hit it with a hammer, and it worked. From 2009, it was a cutoff that they couldn't use asbestos anymore, and that's where the problems came in. And that's where the guys were actually forced to go onto a material they were unsure of. You know, if you have a look at CAF was first developed in 1896. It went commercially available in 1899. You know, gasket technology doesn't change a hell of a lot. So essentially in 2009, you know, they had 110 years experience with asbestos. All of a sudden, this green stuff comes in and guys don't know how to handle it, and, you know, things were failing. So it did create a problem. And yeah, the guys are working through it better now. But you'll notice from 2009, there's a lot more focus put on calculating torque values, determining gasket stresses, controlling joint integrity, because the materials we're using now is more application specific, which makes it more important to actually understand gasket properties and how they can work for you on the plant.
Okay, thanks very much for that answer. Ryan, I see there's another question from Gert B. Gert, if you can go ahead.
Thank you, Dave. Hi, Ryan. Thank you for the opportunity. Ryan, I have 3 questions here for you. That spiral wines, that sitting stress is 69 MPa. That was determined in the early 1950s. Is that still that value, or has it changed?
Okay, in the latest ASME B1620, they have changed that specification. So your 69.9 is actually your Y value from your ASME gasket factors that's used in the ASME 8 pressure vessel code. In the latest ASME B1620, which is the semi-metallic or spiral wound code for ASME, they have specified that, that they've given you a quality control that for certain classes or pressure classes, that seal element must compress by a certain amount with a certain load or stress on it. So they have tightened that up. I believe it's sitting at about 54 MPa, depending on your size, it does change. So it's about 54 MPa that gasket must now compress and create a seal. So, you know, I hate working with minimums. It's very easy to determine a stress on a gasket. It's not so easy to calculate what the relaxation on that flanged assembly would be. But yeah, there are a couple of numbers that are thrown around. When you manufacture the spiral wound, you have to quality check it so that your various classes do compress at a required load. For general, how can I say, ease of use, I like to use 69.9 MPa. I'd rather put a little bit more load on a gasket than too little. And what we like to do is we say, all right, well, 69 is a seating stress. In a practical point of view, we would not like to see a residual gasket stress of less than 80 MPa on a spiral wound. So we do build in safety factors to actually overcome that and to make sure that we get a long-term seal. Typically, from a practical point of view, if we're calculating bolt loads and gasket stresses for spiral wounds, in a typical assembly, I'd like to see a residual stress on a spiral wound between 110 and 130 MPa. That gives you a long-term seal. I've seen spiral wounds, I mean, it was 2 years ago, I was at Chevron, not Chevron, Petro SA. They pulled out a spiral wound, brought it to me. That spiral wound actually had a yellow guide ring. Now, Klinger have not manufactured a spiral wound with a yellow guide ring since 1998, 2018. That's 10 years service, and it wasn't a gasket problem, it was a valve problem. So yeah, getting the possible and as safe as possible is the key to actually getting longevity out of your flanged assembly, such that once all the stress relaxation has occurred, you still have a fair factor of safety to overcome any sort of process mishaps like pressure spikes, temperature spikes, shutting down, breakdowns, that sort of thing.
Okay. Can I ask a second question, Barry?
Yeah, go wild.
Yes.
Married, my wife asks me questions all the time.
The second question is, say for example, you have again an ASME flange, class 150, and you have a spiral wind gasket in it, and you increase the torque. Which will fail first? Will your gasket crash, or will your buckle, your flange buckle, or fail?
6 to 1 1/2 dozen of the other. In your bolt load, there are weaker flanges, things like your 3-inch, your 6-inch, 8-inch, 16-inch, 20. You have limited bolt load. So what will happen is you'll actually strip your bolts before you do any damage to the flange or any damage to the gasket. As you go up in pressure classes, you find your class 300 has a very, very good balance between gasket stress and bolt load and flange rigidity. When you get to your class 600, you find that the available bolt load is huge compared to your gasket area. And you find with your class 600s, with spiral ones, what you tend to do there is you actually start overstressing the compression stops. So you actually start causing your inner ring and your outer ring that's protruding onto your raised face. You actually start extruding those. And you'll find your guide ring on the outside will actually start dishing. It won't be flat anymore. It'll actually start dishing or cupping. So on class 600s, you find that you've got too much load and now you start crushing the gasket. So, there's a number of failure mechanisms throughout all the pressure classes. Generally speaking, when you start getting to your higher sort of pressure classes, you do start finding that the limiting factor is actually your gasket, and not the seal area of the gasket, but actually the compression stop of the gasket. On your smaller sort of flanges, you'll find that it's generally the available bolt load that is limiting, so it's the yield stress on your bolts. That's why we normally recommend, if you are building stainless steel lines, even for lower pressure applications, rather go with a class 300 flange than a class 150 because it does have more available bolt load.
Okay. Pierre, my last question is, Ryan, when you from Klinger do a torque value calculation for us, is that calculation based on the ASME methods, or what method? What is that method based on?
It's very, well, put it this way, it's pretty much based on ASME PCC 1. I think it's Appendix O, discusses how to determine a target bolt load. You don't determine the torque, you determine the target bolt load. What our methodology there basically is, we'll have a look at your seal area. We'll then consult the gasket and see what your minimum gasket stress should be, what your maximum gasket stress should be, and we'll try and target the maximum gasket stress. We leave a safety factor of about 15% in it. So, if your maximum gasket stress is 100 MPa, for instance, we would target something like 85 MPa. Just try and get it as high as possible without any potential damage to the gasket. What we then do is we take the internal pressure, so your design pressure. We don't work with operating, we work with design. So we'll take your design pressure. What happens is your design pressure relieves load from the gasket and adds load to your bolt. So we add that hydrostatic end force caused by the internal pressure onto the bolt load. What we then do with the bolt load is we check that load and your bolt stress against the yield stress of that fastener material at your design temperature, to make sure that, what we essentially do is we assume there is no stress relaxation on startup. And we make sure that the bolt doesn't go into yield when you start approaching design temperature. What we also do is we make sure that the stress you applied ambient on your gasket, once you apply an internal pressure, that actually relieves load from your gasket, and we make sure that when that load is relieved from your gasket, the residual gasket stress is still high enough and still has a fair safety factor above your seating stress to ensure a long-term seal. So, generally what we do is we consider all these factors, and the best way to get the tightest seal is to target the weakest link. So whatever's the weakest, we target a safe number as close to its maximum parameter as possible to get the tightest seal we can. That's why you'll very seldom find us publishing things like torque charts and that sort of thing, because the minute your gasket material changes, the maximum minimum stress of the gasket changes. The minute your bolt material changes, your yield stress changes. The minute your temperature changes, the yield stress changes. We're not even getting down to things like change in bolt lubricant and coefficients of friction. So, if you guys are battling with any problems, or you have anything that you're just battling to fix or seal or sort out, send me information. What I like to do is do an individual calculation for each and every flange joint, unique to where they are designed to work or operating. What I normally do, I get involved a hell of a lot on shell and tube heat exchangers. I'd take a heat exchanger and I'd work out the torque values for all the girth flanges. I'll then recommend the torque values for all the nozzles and drains and you name it, vents. And we actually create a data pack and give it back to the customer as a data pack. So there's a bunch of drawings. There's your data pack. There's all the information you need, all the bolt loads, carry on.
Thank you.
Thanks, Gert, for posing those questions. I just want to go, I don't see any other questions in the chat. Anyone else with a question? Just the final round. Anyone with questions? All right. I think that our questions are up. No one else has questions. But Ryan, and then, okay, then we can close tonight's meeting or technical talk. I want to thank you very much for coming on and making time available to come and have a chat with us on gaskets and gasket selection, gasket materials. I think it was very interesting. It was an interesting chat, and also for those of us in the field of process plants, it does, and working as engineers, it does give us a bit more background, and we'll definitely consider a few additional aspects to flange design and gasket selection in the future. And thank you very much for that, Ryan, and thank you for hosting us. And I see you did post your details on there, and we'll definitely come in touch with you if we need
pleasure,
more information.
Yeah, no, great. Thanks for having me, Gus. And yeah, if you need a hand, or you want to have a chat or anything, don't be shy. Drop me a line. Yeah, always available.
All right, 100%. Thank you very much, Ryan. And,
okay.
And then just something I forgot, the CPD validation code I've just posted in the group chat, so you guys can find it there. Thank you very much, everyone, for attending, and have a good night.
Thanks, Perry. Thanks, Ryan.
Thanks, guys. Pleasure, man. Bye.
Bye. Bye. Bye.